1965 was a successful year for space science and applications. There were the spectacular results of the Ranger and Mariner missions and the other significant accomplishments which advanced our programs toward their objectives. These objectives are to explore the moon, the planets, and the interplanetary environment of our solar system, to investigate the sun and its relationship to Earth, the geophysical properties of the Earth, and the physical nature of the universe, to determine the biological effects of the space environment on Earth life forms, and to search for and analyze extraterrestrial life, to develop experiments for manned space flights which use the special capabilities of the trained astronaut as a sensor, manipulator, and evaluator, to provide pre-doctoral training for scientists and engineers, and grants for space science research projects and laboratory facilities to best use university resources for the national space effort, to develop and manage launch vehicle systems on which reliable space transportation for all payloads depends, to conduct research and development on meteorological satellite systems and support the Weather Bureau in applying them to an operational system, to develop and apply space technology to other practical satellite applications, such as communication and navigation. In April 1965, one accomplishment in communications was the NASA turnover of Sycom 3 and Sycom 2 to the Department of Defense for their operational use. The basic engineering data planned for them had been largely collected. Sycom 3 was launched in 1964 and maneuvered into the world's first stationary orbit at an altitude of about 22,300 miles over the mid-Pacific. Sycom 2, launched into the world's first synchronous orbit in 1963, was moved in 1965 to a new station above the Indian Ocean. Now both communications satellites are serving the Department of Defense for voice and teletype to Southeast Asia. Experiments in air-to-ground communications by satellite were successfully conducted in January between a ground station and a Pan American Airways aircraft in flight over the Pacific. The two-way airborne terminal communicated via Sycom 3 with the California ground station from a position as far away as Hong Kong. And also in 1965, communications for Gemini manned space flights were routed through the Sycom 3 spacecraft. Early Bird, the first commercial communications satellite, was launched by NASA in April for the Communications Satellite Corporation on a reimbursable basis. The payload was a direct outgrowth of Sycom developments. The first Early Bird inaugurated live transatlantic programs in April. It also made possible the live television transmission of the Gemini 6 and Gemini 7 recoveries from aboard the carrier Wasp. This used the type of transportable ground station first developed for NASA's communications satellite program. In 1965, the first prototype model of an applications technology satellite was produced under the direction of Goddard Space Flight Center. This program is a major NASA effort in communications, navigation, and meteorology. It is concerned with the advanced technology of gravity gradient and spin-stabilized orientation systems. It will also be used for antenna research and the determination of environmental effects on components. Technology experiments for the first flights have been selected, and initial flight is scheduled for 1966. Most significant accomplishment of the meteorological program in 1965 was Tyros 9, which rolls through space like a cartwheel, taking weather pictures of the entire world each day. The Delta vehicle, used in launching Tyros 9, has successfully launched 31 satellites in 34 attempts. This includes a remarkable record of 22 successful launches in a row. Once in orbit, ground commands triggered the delicate turning maneuver which put Tyros 9 over on its side. Tyros 9 was put into a nearly polar orbit over the rotating Earth so that it can photograph the entire world each day. The satellite was programmed to take 400 pictures daily. Each day's coverage is converted to neph-analysis maps, which show the storm fronts all over the world. These are made available to weather forecasters for their analyses. The wheel configuration of Tyros 9 will be used in the series of operational satellites developed by NASA for the Weather Bureau. This system will be known as TOS. Some satellites will carry cameras for automatic picture transmission to small receiving stations all over the world. Others will carry an advanced Vidicon camera with tape storage to send back its global observations to the United States. In July, NASA launched Tyros 10 for the United States Weather Bureau. This latest Tyros joined Tyros 7, 8, and 9 in space and marked the first time that 4 weather satellites were operating simultaneously. In September, all 4 storm trackers photographed Hurricane Betsy, making it the best followed hurricane in history. Tyros 7 entered its 3rd year of operation, 4 times the expected lifetime for a weather satellite. Another use for Tyros was weather monitoring before and during the 8-day Gemini 5 manned spaceflight. Because of a Tyros-based forecast of impending storms in the recovery area, the mission was shortened by 1 orbit. Nimbus is now the focus of advanced research and development in the meteorological program. Work on the 2nd flight model continued throughout 1965 under the direction of Goddard Space Flight Center. Scheduled for launching in 1966, Nimbus will carry both daytime and nighttime camera systems. An attractive feature of the next Nimbus will be the ability of small, relatively inexpensive ground stations to receive live pictures during the daytime as well as infrared pictures at night. 1965 has seen notable accomplishments in the lunar and planetary programs. These include the completion of the successful Mariner mission to Mars, the first flight of the new Pioneer series of interplanetary missions, and the success of the last 2 Ranger photographic missions to the Moon. The extraordinary pictures sent back from the successful Ranger 7 mission caused substantial modifications in earlier theories about the Moon. They resulted in lunar maps and models of an accuracy and scale to within a few feet. The area within the sea of clouds which Ranger 7 photographed was renamed Mare Cognitum, the known sea. Ranger 8 target areas were re-evaluated according to Ranger 7 findings. It was launched in February from Cape Kennedy by an Atlas Agena. The Agena has provided NASA with a versatile vehicle system. Since the beginning of 1964, 10 out of 11 launches were successful. The Ranger 8 mission achieved its objectives. Not the least of these was the further qualification of the sophisticated and highly accurate guidance and command systems, and of camera technology. These systems performed at their peak when Ranger 9 was launched successfully in March. As it approached the Moon, it sent back from its 6 cameras more than 5,800 pictures of the lunar surface. Here is a speeded-up sample. Ranger 9 marked the completion of the successful program managed by Jet Propulsion Laboratory for NASA. We have learned a great deal from this program about the topography of several lunar areas. For example, we know that the lunar surface within a crater like Alphonsus is remarkably similar to the surface of Mare Tranquillitatis and Mare Cognitum, photographed by earlier Rangers. If firm enough, these surfaces may be suitable for the landing of the unmanned Surveyor and the manned Lunar Excursion Module. The dark halos around the small craters in Alphonsus suggest past or present volcanic activity. The spectacular final photos of the Ranger 9 approach to Alphonsus were seen live on television by millions of Americans as they were taken. They had a resolution of better than 1 foot just before Ranger 9 impacted, within a mile of the target. Continuing study of the Moon's topography will be accomplished by Lunar Orbiter. In 1965, a prototype model was completed and began testing. First Lunar Orbiter flight is scheduled for 1966, using an Atlas Agena D launch vehicle. Photographic reconnaissance will be its prime task, and there is considerable flexibility in the way the photographs can be tied together. Last year, 10 potential areas were selected for coverage by the first mission. They include examples of all the major types of the Moon's surface to permit assessment of their suitability for spacecraft landings. Each is 22 miles wide and 58 miles long. 9 of the 10 sites are within the area proposed for Apollo manned landings. Lunar Orbiter will approach within 29 miles of the lunar surface at perigee and may remain in orbit for up to 1 year. This should make it an ideal vehicle to obtain scientific data as well as extensive photographic coverage. The end of the year saw the first flight model of Surveyor in final system test prior to shipment to Cape Kennedy. Surveyor is our most complex unmanned lunar exploration project. It is designed to make a soft landing on the Moon and provide a wide variety of scientific data, as well as to survey areas on the lunar surface as possible landing sites for manned missions. This flight model Surveyor and the prototype which preceded it underwent qualification testing throughout 1965 under the management of the Jet Propulsion Laboratory. The spacecraft was subjected to vibration tests. It went into a simulated space environment in the solar thermal vacuum chamber. With its ground support equipment, the prototype was shipped to Cape Kennedy. Here, it was used to check out launch facilities and procedures. Then it moved to Goldstone Tracking Station in the California desert. Here, it underwent compatibility testing with NASA's Deep Space Network. On November 22nd, a most significant milestone was passed in the Surveyor program. A T-2N terminal descent test vehicle performed successfully in a combined tether and descent test at Holloman Air Force Base, New Mexico. Prime objectives were to verify the soft landing capabilities of the Surveyor spacecraft and evaluate critical flight parameters in the velocity sensor, flight control, and vernier engine subsystems. You will note that once the vehicle was released from the balloon, there was no discernible displacement in pitch, yaw, or roll. This stable descent attitude was maintained by the constantly varying thrust output of the throttle-controlled engines, responding to the commands of the flight control subsystem. After release, the vehicle automatically adjusted to the planned descent trajectory until a constant descent rate of 5 feet per second was reached. This constant descent rate can be seen as the time when the stabilizing chute fell to the side of the vehicle. In effect, the spacecraft made a simulated lunar surface landing and was recovered by parachute at an altitude of 500 feet. From this first successful performance of the model, we can conclude that the design is adequate to guide the spacecraft to a gentle landing on the Moon. The system will, however, undergo further testing. Many problems, managerial and technical, were overcome during this year of qualification and test. Now, a Surveyor spacecraft is nearing flight acceptance for the first mission in the most difficult project yet undertaken in the Space Science and Applications program. Centaur, launch vehicle for Surveyor, has completed the first phase of its development program with a successful launch in August carrying a Surveyor dynamic test model. Centaur is now fully qualified to meet Surveyor direct descent requirements. The two-burn development phase to put Surveyor into parking orbit should be completed late in 1966. Going beyond the moon, the planetary program in 1965 saw successful completion of the Mariner Mars mission. Mariner 4 had to be launched under pressures set by the inexorable timetable of celestial mechanics, which provide only a short window every 2 years during which a Mars mission could be launched. The first attempt was unsuccessful due to a faulty shroud. But 30 days later, in November 1964, Mariner 4 was successfully launched with a redesigned new shroud, on time for its historic 228-day journey to Mars. On its way, Mariner 4 gave us our first look at interplanetary space between Earth and the orbit of Mars. It found it very much like that between Earth and Venus, with one big exception. A notable peak in the impact rate of cosmic dust activity was recorded on the monitors of the Mariner project. This and other interplanetary experiments returned almost 20 million such scientific measurements during the course of the flight. On the 307th day of flight, when it passed beyond effective range for data transmission, Mariner 4 was 191 million miles from Earth, a standing record. It will have a useful life that may extend beyond 1967. As it passed close to Mars, Mariner 4 measured no evidence of radiation belts, such as we have near Earth, and no significant magnetic field. This and the lack of such features as mountain chains suggests that Mars, unlike Earth, may have a solid core. In July 1965, as the crucial flyby approached, tracking stations of the Deep Space Net around the world and the scientists at Mariner Control coordinated the final commands that turned on the cameras. At a range of 10,500 miles, Mariner 4 began to take its pictures. There were 22 in all, and they would cover 1% of the surface of Mars. The picture data were stored on magnetic tape for later playback to Earth. As the spacecraft moved behind Mars, changes in the radio signals passing through the atmosphere of Mars were recorded. This occultation experiment showed the Martian atmosphere to be very thin and revealed the existence of an ionosphere. Picture information in digital form started to come in at 6 a.m. Pacific Daylight Time on July 15, 1965. Converted to shades of gray, this is what the first picture looked like. A revelation comparable to Galileo's first view of the moon through a telescope. There were 22 pictures taken, the last at a range of 7,500 miles. There was scant evidence of erosion, suggesting that the Martian surface may be as it was 1 billion years ago, with very little water present since that time. Perhaps the best is this one, showing the craters, probably caused by meteors, distributed on Mars in a pattern remarkably similar to that of the moon. After picture playback, Mariner 4 returned to reporting on interplanetary space, with good data received up to last October 1st. Improved ground facilities may make it possible to resume tracking in 1966, and we hope for more good data when Mariner 4 again moves nearer Earth in 1967. The Mariner mission answered many questions, but the big one, is there life on Mars, must wait for Voyager's surface explorations. Mariner data will be used in designing Voyager and in devising the experiments it will carry. Voyager is designed to explore Mars by automated spacecraft. and landing capsules which may be later adaptable to other planetary exploration. In 1965, the first part of design definition for the Voyager spacecraft system was completed by each of 3 contractors. The Voyager spacecraft system will orbit Mars to make measurements similar to those made by our Earth satellites. The spacecraft is also intended to carry instrumented capsules, which can land on the Martian surface to make direct biological, geological, and meteorological measurements. Voyager will require planetary quarantine of the landing capsule. In 1965, tests began with a new tool to guard against contamination. In bioclean rooms like this experimental facility, instruments destined for planetary landings may be assembled with minimum risk of bacteriological contamination. This is assured by a laminar flow of clean air from ceiling to floor and by continuous monitoring. Meanwhile, significant planetary exploration continues with a new series of Pioneers under management of Ames Research Center. On December 15th, Pioneer 6 was successfully launched from Cape Kennedy by an improved Delta launch vehicle. This first of the series carries experiments in cosmic rays, magnetic field, solar plasma, and radio propagation. It will send back measurements from up to 100 million miles away in the regions between the Earth and Venus. In 1965, man in space made significant contributions to scientific knowledge. During the Gemini flights that year, astronauts performed a wide array of scientific, applications, and technology experiments. Most spectacular has been the color photography from the Gemini spacecraft. Photographs like these have immense potential for the study of geology, water resources, glaciers, oceanography, meteorology, forestry, and even agriculture. Physiological and biological experiments, in which the astronauts were either subject or experimenter, demonstrated effects of the space environment on man and other forms of life. Some 30 experiments are in preparation for Earth-orbiting Apollo missions, and 10 experiments are defined for emplacement on the lunar surface by an astronaut. These future manned space experiments will require specialized scientific training. In 1965, 5 scientist astronauts were selected and started their training. They are Dr. Owen Garriott, ionospheric physics, Dr. Curtis Michael, nuclear physics, Dr. Harrison Schmidt, geology, Dr. Edward Gibson, engineering physics, and a medical doctor, Joseph Kerwin. Many projects within the complex bioscience program relate to manned space flight, lunar and planetary exploration, or deep space probes. Accomplishments of the bioscience program in 1965 touch upon all of these areas. The first flight model of a biosatellite is now being built and tested. Ames Research Center, manager of the biosatellite program, has assisted experimenters to prepare 13 experiments for the first biosatellite flight, a 3-day orbit. Time-lapse photography shows the test cycle for some experiments to be carried. The effect of weightlessness on growth and movement will be studied using the pepper plant and wheat seedlings. Embryological development will be studied using frog eggs, and the effects of weightlessness will also be studied on the single-celled amoeba. 7 experiments will be flown to study the combined effects of weightlessness and radiation. Bacteria, mold spores, plants, and several insects will be used. This mock-up of the biosatellite shows the spacecraft and experiment configuration for the 30-day mission. In addition to the 3-day flights, the biosatellite will orbit the Earth for periods of 21 and 30 days to determine the effects of the space environment on human cells, rats, plants, and monkeys. The Physics and Astronomy program is of fundamental importance to our national space effort. A family of orbiting observatories under management of the Goddard Space Flight Center is a major element in that program. The first orbiting geophysical observatory was launched from Cape Kennedy in 1964. The second went into a nearly polar orbit from Western Test Range in October of 1965. Both had trouble in orbit. OGO-1 because two booms failed to deploy, and OGO-2 because of horizon orientation problems. Both were officially failures. They must, however, be considered very successful failures based upon the quality and quantity of the data they continue to return. OGO-1 is still operating 15 months after launch. OGO-2, in orbit only a few months, has returned less data, but completed many successful orbits in the fully stabilized and pointed modes not achieved by OGO-1. It continues to give good data in its present spinning mode. Both OGOs have proven their capability to make a broad spectrum of measurements at the same time in the same place in the previously more or less separated fields of ionospheric, plasma, atmospheric, trapped radiation, and magnetic field research. A third OGO has been completed and is now undergoing tests at the contractor. Experience gained with the first two spacecraft has been incorporated into the design and test of this OGO. It will carry the same experiments as OGO-1 and will be launched early in 1966 from Cape Kennedy. The Orbiting Solar Observatory, OSO, is very important to the Physics and Astronomy program. In orbit above the Earth's atmosphere, it can observe the effects of the Sun on Earth and interplanetary space without the blocking effect of the Earth's atmosphere. Orbiting solar observatories carry a number of complex experiments devised by scientists in NASA, other government agencies, and universities. OSO-2 was launched in February 1965 and successfully placed in orbit. 7 of the 10 experiments aboard returned new and useful information on the condition of the Sun at solar minimum. This included measurements on the solar output in the near ultraviolet, X-ray, and gamma-ray regions. In November, OSO was placed in a stowed mode, where it is coasting on its own, so that we may examine its magnetic attitude. OSO-2 can be reactivated at a later date when solar conditions have changed. OSO-3, launched in August, failed to orbit and was lost in the South Atlantic. The experiments lost will be duplicated in the 5th OSO. The 4th and 5th OSOs, scheduled for flight, are in various stages of fabrication and test at the contractor plant. Our present knowledge of the Sun has shown clearly the need for a higher precision, higher capacity spacecraft for the study of solar phenomena. Last year, an engineering model of an advanced orbiting solar observatory, AOSO, was completed. The stabilization and guidance system is being built, and its sun sensors are presently under test in a laboratory still room. Experiments have already been selected for several AOSOs. Astronomy, the study of the universe, achieves a new dimension with the ability to put instruments above the Earth's atmosphere. Here, they may measure gamma ray, X-ray, ultraviolet, infrared, and radio wave radiation that cannot reach the ground. In 1965, after 5 years of exceedingly difficult development work, the first orbiting astronomical observatory was being readied for flight. The experiment packages have been tested and integrated into the first flight model. Each OAO will carry the experimental packages of such institutions as University of Wisconsin, Goddard Space Flight Center, and many other scientific agencies and universities. The prototype model completed its qualification tests at the contractor. It is being modified to serve as a later flight spacecraft. Thus, the past year saw marked progress toward providing an observatory in space which can be used by numbers of astronomers, free from the blanketing and distorting effects of the Earth's atmosphere. In 1965, 5 additional Explorer satellites were launched. One of the most important scientific discoveries of the space age has been the Earth's magnetosphere, the region of influence of the Earth in space. It was suspected from the results of experiments carried by early Pioneer and Explorer satellites, and confirmed by Explorer 14 and the first interplanetary monitoring platform, IMP. In May, another IMP, Explorer 28, joined previous satellites to continue study of interaction between the Earth's magnetic field and the solar wind, begun by the first IMP in 1963. In particular, they are exploring the shock wave and transition region on the sunward side of the magnetosphere, and the extended tail with its neutral magnetic sheet on the night side of the magnetosphere. In April, a Beacon Explorer 27 was put in orbit. It is measuring the Earth's gravitational field through Doppler tracking. In addition, its transmitters provide to observers in 36 nations synoptic data on the electron content of the atmosphere. This is a major element in our international scientific program. Another explorer, launched in 1965, was the geodetic satellite GEOS, built by Johns Hopkins Applied Physics Laboratory. It is an active satellite containing flashing light electronic systems and laser reflectors for detailed study of the Earth's gravitational field and a reference for precision mapping. It was successfully launched in November by an uprated version of the Delta launch vehicle, which was being flown for the first time. Also in 1965, a passive geodetic explorer, PAGEOS, was inflation tested in Lakehurst, New Jersey. It will be launched in 1966. Some satellites built by other nations were launched by NASA in 1965. The ISIS-X was launched in late November. It combined the Canadian Alouette B with the NASA DMEA Direct Measurement Explorer in a piggyback configuration for ionospheric studies. Already, the results of this completely successful experiment have added considerably to our knowledge of the ionic sheets surrounding the spacecraft. The two are orbiting within approximately 1 mile of each other, conducting related measurements. Also, the DMEA Explorer has demonstrated successfully a novel magnetic attitude control system that should be useful for many future scientific missions. The French FR-1 was launched in December. It will investigate very low-frequency radio signals in space. FR-1, like ISIS-X, was launched by Scout, NASA's only all-solid space vehicle. Scout has been used extensively in launching spacecraft for NASA, Department of Defense, and international organizations. There have been 39 launches since 1960. The last 12 consecutive firings have been successful. Like explorers, the sounding rocket is an economical, reliable, and versatile tool. In 1965, approximately 130 were launched to continue the investigation of our atmosphere and to carry out exploratory space experiments. In February and March of 1965, the year of the quiet sun, 77 sounding rockets were launched from the military sea transport Croatan. Launchings took place along the west coast of South America from Colombia to Chile. The Mobile launch expedition was managed by NASA's Wallops Station, and the experimenters came from NASA centers, other government agencies, industrial laboratories, and universities. scientists and government officials were welcomed at many of the ports visited. Over 95% of the launches were successful. The most important of the scientific accomplishments was the ability to conduct our first rocket measurements of the ionosphere from equatorial regions. Sounding rockets have been launched for scientists of many nations at Wallops Station, Virginia. In August 1965, an international meeting was held there under NASA auspices to set up an inter-American meteorological rocket network. NASA's Sustaining University program is providing grants nationwide for graduate training, scientific research, and laboratory facilities that support and encourage fundamental space science research in the academic community. In 1965, more than 3,000 pre-doctoral students worked under NASA training grants. They were in universities in each of the 50 states. 70 received their PhDs during the year and are doing teaching or research in government, industry, or universities. During the year, Sustaining University program research grants totaling more than $13 million were made to 45 universities located in 27 states. Their interim or final results were a significant factor in space science accomplishments. Space science and engineering laboratories, wholly or partly funded by NASA, were put into service at 12 institutions during 1965. 5 more had been previously completed, and another 16 are underway. The academic community joins with industry and government in the national space effort. And a national effort it is. Scientists and researchers from the colleges and universities, engineers and scientists, administrators and technicians at contractor plants throughout the country, and the scientists, the project managers, the engineers and technicians at NASA field and launch centers, this is the team. These are the men who made 1965 a year of success for space science and applications. Some of the highlights: there were new uses for communication satellites already in orbit, and meteorological satellites with the capability for greatly increased weather coverage were placed in orbit. Useful results came from the scientific and technological experiments programmed for astronauts during manned space flights. And there was progress in the development of a biosatellite to carry other life forms and experiments into the space environment. Centaur, NASA launch vehicle for Surveyor, was launched successfully to complete the first phase of its development program. It was a year in which our knowledge of the Earth, the Sun, and the physical nature of the universe was increased by the scientific information returned from orbiting laboratories, and by explorer satellites, Pioneer space probes, and various sounding rockets. Our most spectacular successes were the lunar photographs of the Ranger series, and the pictures made by Mariner 4, which gave man his first close look at the surface of Mars. These were highlights of 1965. Now, we look to the future, to the new challenges and the continuing opportunities in that limitless laboratory, space.